So in today's lecture, we discuss about the Newton's law in Cartesian as well as in polar coordinates. So we are all familiar with these Newton's equations, Newton's law. So the Isaac Newton was the first one to introduce the concept of mechanics, and he was the first one to establish all the dynamic systems in terms of mathematical representation. Newton's laws are very, very crucial and have a great impact on many dynamical systems, especially as long as we consider it as a classical object. So for all classical objects, we can employ this Newton's laws and its equation of motion to solve the dynamical systems. Okay. So Newton's laws in Cartesian as well as in polar coordinates. So that is the lecture that we are going to discuss. That's the topic we are going to discuss now. So this is very much interesting. In fact, the reason is I already told you, right? He was the first one to introduce the concept of dynamics. So solving, making a system or creating a system, a moving object, dynamical systems, and solving it for a solution is really, really wonderful in the framework of Newtonian mechanics. Okay? So we have some familiar ideas about the coordinate systems, etc. And we try to connect these coordinate system, and we try to create a equation that represents the dynamic. Okay. So this is the system. This is the representation of Newton's laws in Cartesian system. So we have an x, y, z coordinate system. We consider a plane, x and y plane. In that plane, a particle is keep on just moving. The particle is just moving in this plane. And please notice that this blue line shows the trajectory of the particle. That is the movement of the particle or the path tracked by the particle, path of the particle traced out by the particle. And I have given two different positions. Here one position, and we have another position here. These two are the position of this object at any instant of time. Okay? These are the position of the object at any instant of time. And at certain instant of time, let me call this as P. The position of the object is at P, which is a function of xy. This position carries two coordinates, x coordinate and y coordinate. Okay? This function carries this point, this particle located at this point, associated with two coordinates x and y. So I put it as a P as a function of x and y. Okay? Along the x direction, I have a unit vector x cap, and along the y direction, I have another unit vector y cap. So this is completely the Cartesian coordinate system. Okay? This is the complete Cartesian coordinate system. In Cartesian system, the position of the particle is represented by x and y. In Cartesian system, the position of the particle is represented by x and y. Therefore, we have this vector p, that is OP vector. The position vector of this particle at p is given by OP vector, that's equals to r vector, that's given by x component multiplied by x cap plus y component multiplied by y cap. Okay? So x into x cap plus y into y cap gives you the position vector of this particle at point. Okay. So x cap and y cap are the unit vectors pointing in the increasing direction of x and y. And of course, x cap and y cap are orthogonal to each other. They are perpendicular to each other and points in the same direction everywhere or for any locations. So with this, we can say what is the velocity. Once I know what is the position vector of this particle, then I can find what is the velocity vector. So velocity vector v is equivalent to dr by dt. I simply derive this, take a derivative of this r vector with respect to time. That gives me the velocity vector. Because r is in fact a function of time itself. So as time increases, this r also changes. Therefore, I can surely differentiate this position vector r with respect to time. Therefore, I will get velocity vector. So velocity in Cartesian system is given by v equals to dr by dt. That's equals to d by dt of the same r vector. You replace this, you substitute this r vector here, this r vector here. Therefore, x dot x cap plus x into dx cap by dt plus y dot y cap plus y into dy cap by dt. But we know that x vector and x cap and y cap are unit vectors. Therefore, it becomes 0, right? If we differentiate that, it's a constant vector in fact. If you differentiate that, it becomes 0. Therefore, you'll get dx by dt is equals to dy by dt. That's equals to 0 here. Therefore, you are left out with the velocity vector v equals to x dot x cap plus y dot y cap. Therefore, the acceleration is given by, again, you have to differentiate this velocity vector with respect to time. That gives you the acceleration of the moving particle. So you'll get x double dot x cap plus y double dot y cap. X double dot and y double dot are simply the second order time derivative of the x and y with respect to time. Therefore, Newton's second law in vector form can be written as the any force vector is equals to fx x cap plus fy y cap. That's equals to mass times the acceleration, but acceleration is the velocity derivative for m into x double dot x cap plus y double dot y cap. Okay. So this is the force equation we have derived in Cartesian framework. Next, we move on to the plane polar coordinates. Okay. Next, we move on to the plane polar coordinates. This side, same. Let us assume that the vector p, OP vector, the position vector of the object, is making an angle theta with respect to the x-axis. And let us assume that OP vector is a constant vector, therefore the magnitude of this vector is r, and it is making an angle theta with respect to the x-axis. So each point p of x comma y on the plane can also be represented by its distance r from the origin O and the angle theta OP makes with the x-axis. Therefore, I can find out what is the relation that connects the r and theta with respect to x and y. Right? So what I can do is I can make a perpendicular drop. I can drop a perpendicular line here and here so that I can get a rectangle. This is one, and I have one more. This right. Here it is, right? So this is y coordinate, that's x coordinate. Therefore, the x coordinate can be taken by r cos theta, because cos theta is this adjacent divided by hypotenuse. Therefore, I will get cos theta equals to x by r. Therefore, x equals to r cos theta, and y is equals to y. The value of y you can get it from taking sin theta. Sin theta is opposite divided by adjacent hypotenuse. Therefore, sin theta equals to y by r. Therefore, y equals to r sin theta. Okay. So r can also be, you simply square this x and y and add up. So you will get what is r. So r is equals to square root of x square plus y square. And also theta can be identified by dividing y by x, so that theta is equals to tan inverse of y by x. Okay. So interesting to note in this presentation is, along the x vector I have a unit vector x cap. Along the y vector I have a unit vector y cap. Okay. Along the unit vector y cap. Therefore, in terms of plane polar coordinates, just like we have x cap and y cap, I can introduce two unit vectors in plane polar coordinate corresponding to the plane polar coordinates, which is r cap and theta. So r cap is a unit vector pointing in the direction in which direction r increases, and theta cap is a unit vector that point along the particle direction, the movement of the particle. If this particle is somewhere here, then the r theta direction goes like this and r goes like this. Okay. So r and theta increases in the increase r cap and theta cap, pointing along the direction in which this theta and r increases. Okay. So for plane polar coordinates, we have two unit vectors, r cap and theta cap. And this r cap and theta cap keep on changing its direction depending on where the point is located on the plane. Unlike in the case of xy plane in the Cartesian system, X cap is always pointing towards in this direction and Y cap is always pointing towards in the upward direction, no matter where the point P is. Whether the point P is here or here or here or here. X cap is always towards the right direction, right side, and Y cap is always the upward direction. But the present case, the unit vector R and theta pointing in the direction of the increasing direction of the coordinate R. If R increases along that direction only, R cap also pointing out, and in which direction theta increases along that direction of the theta cap, the unit vector increases. Okay. Therefore, R vector can be written as R cos theta. This is X component. Therefore, R cos theta X cap plus R sin theta. This is a Y vector. This is R sin theta. That's Y component into Y cap. Okay. Therefore, R cap is equals to cos theta X cap plus sin theta Y cap, and theta cap is equals to minus sin theta X cap plus cos theta Y cap. Okay. This is the corresponding framework of the point P in the polar coordinate system. So R cap is the derivative of this R vector with respect to R. To differentiate this quantity R, so you get cos theta X cap plus sin theta Y cap, and theta cap is derivative of this R vector with respect to theta. So you'll get minus sin theta X cap plus cos theta Y. And of course, just like how X cap and Y cap are perpendicular to each other, similarly, R cap and theta cap are also perpendicular to each other. Therefore, the dot product between them is 0, but the direction depends on the vector. Okay. So once I know what is the position vector R, then I can go for the velocity coordinates in terms of polar coordinates, velocity vector in terms of polar coordinates. Therefore, R vector equal to radius distance. R vector can be written as R into R cap, and the unit vectors in polar coordinates are functions of theta only. Therefore, dou R by cap by dou theta, and dou theta cap by dou theta. So you get this equations, R cap and theta cap. Okay. So velocity vector is equals to dr by dt. Therefore, dr by dt is what is R vector? In fact, R into R cap. Therefore, dr by dt into R cap plus R into dr cap by dt. So you have to use the product derivative, right? Product of the derivatives. So first you differentiate this, keeping the R cap as such, and you differentiate this R cap, keeping the R as such. So that you will get the velocity vector V vector is equals to R dot R cap plus R into theta dot theta cap. Therefore, the radial component R dot and tangential transverse component are R into theta dot. So R dot is the radial component of the velocity vector, and R into theta dot is the tangential or transverse component of the velocity vector. Okay. So once we know what is velocity, and of course we can derive what is acceleration also. The acceleration of the in terms of polar coordinates, to differentiate, we know what is v. In fact, you differentiate this v with respect to time, and you get a vector, the acceleration vector. So you substitute the previous form of the velocity vector, the previous form of the velocity vector here. Finally, you get the acceleration vector A is equals to R double dot minus R theta dot square R cap plus 2 into R dot theta dot plus R into theta double dot theta. Okay. Therefore, that's the so-called the acceleration of a moving object in a plane in terms of plane polar coordinates. So for this acceleration also, we have a radial component. This is given by R double dot minus R into theta dot square, and the tangential component is 2R dot theta dot plus R into theta dot. That gives you the tangential component of the acceleration. Okay. So this minus R in theta dot square is the familiar centripetal contribution, and 2R dot theta dot is called the Coriolis contribution. Okay. Therefore, finally, the force equation F is equals to mass times the acceleration m into dv by dt. Therefore, F is equals to Fr into R cap plus F theta into theta cap. That's equals to mass times this acceleration component. Just write this acceleration component here. Therefore, you get m into the acceleration component. For this also, we have two component. One is the radial direction, it goes along the radial direction. The other one is the tangential directions. Therefore, IFR is equals to m into this quantity, and f theta is equals to m into this quantity. So that gives you the final what is the force component in terms of the plane polar coordinate systems. Following this, we have a few questions. So define inertial frame, non-inertial frame of references. What is mean by Galilean invariance? Give the expression for Galilean. So these are few frames questions that we you can answer. Okay. Thank you.